Welcome everyone. Today I'm going to introduce Visual Acuity, an innovative application designed to assist healthcare providers with routine eye testing in Thailand. Now, before diving into our application, let's briefly understand what Visual Acuity is. Visual acuity is a measurement of how clearly a person can see at a specific distance. It's typically assessed using standardized charts with letters or symbols of varying sizes, such as the Snellen chart shown here. This chart has been a standard tool in optometry for decades. Now, how to measure. The process of measuring visual acuity follows a standardized procedure. Typically, the patient is positioned 20 feet away from the chart. The eye care specialist will ask the patient to cover one eye, and then read increasingly smaller rows of letters or symbols until they can no longer see them clearly. This process is then repeated with the other eye. This simple test helps identify refractive errors and other vision problems. Now, let's address the real-world problem our application aims to solve. In Thailand, healthcare providers, especially nurses, are overwhelmed by high patient loads. Thailand has only 2.14 nurses per 8,000 people according to WHO's 23rd data. While vision tests are conceptually simple, they are repetitive and time-consuming. Manual checking of what number do you see takes valuable time that could be used for more complex patient care. This is especially challenging when dealing with elderly patients or children who may speak imperfectly, requiring repeated clarification. Now, what is this app? Our solution is a voice-activated, digit-based eye test assistant designed specifically for Thai hospitals and clinics. The app shows a number between 1 to 9 to the patient, and the patient must speak the corresponding Thai word. For example, if the image shows 2, the patient would say 2, which is 2 in Thai. This simple system automates a routine part of vision testing. Now, let's talk about the app features. The app works through 3 key processes. First, it uses OCR, or optical character recognition, to read the number from the eye test image. Then, it employs speech recognition to accurately transcribe what the user says in Thai. Finally, it validates whether the spoken word matches the expected response using lightweight natural language processing logic. Now, our application leverages 3 pre-trained models, each handling a different modality: image, audio, and text. For the visual components, we use EasyOCR to extract digits from the test images. For audio processing, we employ WAV2VEC2 large XLSR53TH, which is specifically fine-tuned for Thai speech recognition. And for text comparison, we use Python's difflib getClose matches function for lightweight text matching with tolerance for slight pronunciation variations. Now, let's look deeper at our first component. We chose EasyOCR for its excellent performance with digit recognition. It processes the eye test image to extract the digit that the patient needs to identify. The framework uses a combination of detection models, recognition networks, and decoders to accurately identify text in images, which is perfect for a use case of reading simple digits between 1 and 9. Here is the framework, and here is the optical character recognition demonstration. Now, we have explored several alternatives before settling on EasyOCR. Tesseract was considered but rejected because it was outdated for Thai and often misreads curved or stylized fronts. Paddle OCR, while accurate, is heavier and more difficult to deploy for us beginners. Or training a custom OCR model would be overkill for our simple need to recognize single digits just from 1 to 9, and would require substantial labeled data. Now, the WAV2VEC2 speech recognition. For our speech recognition component, we selected WAV2VEC2. This model listens to the user voice through a microphone and converts spoken Thai number words like 1, 1, or 5, 5 into Thai text. The output is then compared to the expected answer determined by the OCR component. This model is specifically refined for the Thai language. making it ideal for our application. Now, the alternative considered. We have considered a lot of alternatives, such as OpenAI Whisper, while more accurate, is too large and too slow on CPU and requires GPU or cloud resources, making it impractical for many clinical settings. Google Speech API requires internet connectivity and raises privacy concerns. Or, the Mozilla Deep Speech for Thai was another option, but it's not well maintained and has limited Thai language support. Now, for the next part of our presentation, we will discuss the third component, difflib, which helps our application interpret the patient response even when their pronunciation isn't perfect.
Here's come to the difflib.getCloseMatches. It actually used for the matching spoken word to the expected Thai word. In this case, we use it for a number. There are many alternative tools, which some of them are too heavy, some of them are too meaningful, and some of them are too strict. That's why I use difflib. How they work together, I will explain you step by step. First, we read the image using the OCR to generate what is the number. Second, we have the table to map that number to Thai word. Third, we use the ref to vector to capture our sound and convert it into a text. And lastly, we compare and calculate the score by difflib. Next, internal mapping. We have the digit to Thai to map the text with the digit. Then we can compare using the OCR or the user spoken variable and test the matching by the fuzzy match. Here's the app workflow, which starts by showing an eye testing image, which you could read out loud by answering the questions, which if it doesn't match the score or it couldn't listen correctly, it will ask you to speak again. So when it finishes, it will return the score for you. You can look at the QR code for more details. All the main files are in there, named ANSI 12. Image processing is the ECOCR, text processing are the difflib, and speech recognition are the wave to vector. Our app have the feedback for the real communication, so that's why we need to record all the sound file to be able to give a feedback information. Here's the speech recognition example code. On the right side, there are the code that does the base match over in the case of wrong communication. To boost our app accuracy, we will first leverage the confidence score from speech recognition to ensure reliable transcription. Next, we will enable live camera to input for our more practical OCR. We also implement post OCR filtering to clean up digits, readings, and log all the incorrect responses to learn from our mistake. Finally, we will add user-friendly way to adjust the matching sensitivities for different scenarios. Our app stands out with the built-in Thai language support for both image and speech. The multimodal approach combining image, audio, and text. Unlike traditional single-mode apps, it works completely offline at realities where most competitors require internet. Our lightweight models run efficiently on CPUs to avoiding the heavy resource demand of most models like Whisper or Bird. Finally, our rules-based logic combined with OCR makes the app process easily understandable, contrasting with the often opaque natures of competing applications. Our revenue projections, our initial cost will be around 4,000 Thai baht. It already includes the Raspberry Pi, microphone, and etc. except the software. So we could sell it around 8,000 to 10,000 Thai baht. So in this case, we take 10,000 Thai baht each. So let's say if we sell it to a small clinic for 100 units, we will get 1 million baht. And for the support custom UI, we do it monthly. For it will cost around 20,000 Thai baht. So in 1 year, we will get 240,000 Thai baht.
สวัสดีค่ะ คุณกำลังเข้าสู่ระบบทดสอบสายตาอัตโนมัติ กรุณาทำตามคำแนะนำของระบบค่ะ คุณใส่แว่นสายตาใช่หรือไม่
ไม่
กำลังประมวลผลรูปภาพกรุณารอสักครู่ เริ่มพูดบรรทัดแรกวางเสียงสัญญาณได้เลยค่ะ
8 3
คุณพูด 8 3 ใช่หรือไม่
ใช่
เริ่มพูดบรรทัดถัดไปหลังเสียงสัญญาณได้เลยค่ะ
6 3
คุณพูด 6 3 ใช่หรือไม่
ใช่
กรุณาเปลี่ยนรูปเพื่อดำเนินการต่อกำลังประมวลผลรูปภาพกรุณารอสักครู่ เริ่มพูดบรรทัดแรกวางเสียงสัญญาณได้เลยค่ะ
5 4 4
คุณพูด 5 4 4 ใช่หรือไม่
ใช่
เริ่มพูดบรรทัดถัดไปหลังเสียงสัญญาณได้เลยค่ะ
5 8
คุณพูด 5 8 ใช่หรือไม่
ใช่
คุณเห็นเลขอื่นอีกใช่หรือไม่
ใช่
พูดเลขที่คุณเห็นเพิ่มหลังเสียงสัญญาณ
2
คุณพูด 2 ใช่หรือไม่
ใช่
เริ่มพูดบรรทัดถัดไปหลังเสียงสัญญาณได้เลยค่ะ
4 8 3
คุณพูด 4 8 3 ใช่หรือไม่
ใช่
สิ้นสุดกระบวนการวัดค่าสายตาแล้วค่ะ
As you can see the result picture on the screen at distance 3 meters. That means the screen is 3 meters far away from the person who is testing. And the number 20/70. The 70 means the standardized of normal person who can see the number from 70 feet. But in this case, the person who is taking the test can see at 20 feet. And the number -1 means that at 20 feet, she answered one number wrongly. And here's all our group members and what they are doing. Thank you for listening for our presentations.